Hello everyone, this is Zheng Qingyang from Fuzhou University of China. I'm going to introduce our work, Recurrent Enhancement of Visual Comfort for Casual Stereoscopic Photography. In our work, the goal is to handle a challenging application as shown in the figure. It aims to allow common users to create a stereoscopic photo using two images captured by a handheld monocular camera. This application has been named as Casual Stereoscopic Photography. As shown in the figure on the left, users first take one image, move the camera horizontally and take the second image. However, the captured image pair can hardly satisfy the stereoscopic geometry constraint, let alone maintaining satisfactory composition and visual comfort. To solve this problem, existing methods often treat this as two separate problems: stereoscopic rectification and disparity adjustment. For stereoscopic rectification, they rectify two images by finding a pair of homographies and then using them to transform the two images. The homographies are estimated utilizing either camera-calibrated parameters or epipolar geometry of the acquired images, as shown in the figure above. For disparity adjustment, there are mainly two types of methods for manipulating the disparity distribution of stereoscopic images. First, the disparity mapping methods adjust the disparity range of a scene by scaling it into the comfort zone via either depth image-based rendering or stereoscopic wrapping-based rendering methods. These solutions tend to introduce visually noticeable rendering artifacts when larger disparity change is performed. On the other hand, the disparity shifting methods improve the visual comfort by moving the zero disparity plane of the original scene. Its main advantages are low computational complexity due to its simple rendering process and no rendering artifacts in the processed images. The main contributions of our work as follows. To our best knowledge, our proposed framework is the first learning-based method to enhance the visual comfort of stereoscopic images in favor of the application of creating casual stereoscopic images. Besides, different from prior works, we present a recurrent deep learning-based framework to jointly and progressively handle the geometry constraint and the uncertain disparity range of casually captured images. In our life, we often iteratively adjust scenes and then evaluate our adjustment in order to progressively accomplish certain purpose. Inspired by such behavior pattern, we propose a unified reinforcement learning-based model. It mimics human behavior by recurrently manipulating the left and right views and then evaluating the visual comfort of the resulting stereoscopic image until it reaches the optimal condition, instead of trying to obtain the optimal stereoscopic images directly. Thus, we adopt a cost-to-find methodology. Particularly in the core stage, the state, including left and right images, disparity map, and historical action vector, is sent to the model for transforming images and then quickly evaluate its visual comfort. After that, in the fine stage, we refine the disparity range of the previously processed stereoscopic images by shifting the left and right views to further enhance its visual comfort. From now, let me introduce our model's details stage by stage. In our formulation, the state is consisted of the input left and right views, the disparity of the views, and the historical experience. Especially, we use an LSTM latent layer, which encodes the historical experience by incorporating the previous actions. In this way, the state of the decision-making procedure not only considers the current observation but also involves the historical experience. The model learns the estimation for the optimal value of each action, defined as the expected sum of future rewards when taking that action and following the optimal policy thereafter. An optimal policy is easily derived from the optimal values by selecting the highest valued action in each state. In the coarse stage, we define a set of actions for the network to sample, which can transform the left and right views, including rotation transformations, perspective transformations, and a stopping trigger. The rotation transformation will rotate the left and right views by 1 or 2 degrees, clockwise or counterclockwise. We simulate the camera movements or the perspective transformation by using image wrapping. The image wrapping is determined by the displacement of image corners. According to different camera movements, coordinates of image corners are shifted on the horizontal and vertical axes, respectively. In the final stage, we define a set of actions for refining the disparity range. Without loss of generality, the actions allow us to fix the left view and horizontally shift the right view by multiple scales. Furthermore, the stopping trigger ends the recurrent process of our framework. During training in both stages, two identical deep neural networks are applied for the purpose of sampling the optimal action and determining the value of the policy, respectively. Their weights are denoted as theta and theta prime. After executing the action, we use a weighted sum of structural similarity index and VCA metric to measure the reward, so we can quantitatively evaluate the visual comfort of the produced stereoscopic image as the reward of the action. Then we use the mean square error as a loss function. For experiments, we randomly transform images from stereo image dataset to produce low-quality stereoscopic images as synthetic images. Based on these synthetic images, we evaluate our method in two separate tasks: geometric transformation and disparity shifting. In Table 1, we compare against image rectification methods, including a deep learning-based method. In Table 2, we compare with regression, exhaustive search, and disparity mapping methods. For all the results, our approach generally outperforms others in most metrics. Lastly, we collect a set of real-world images to evaluate our method. We build a dataset containing pairs of real-world images captured by monocular mobile cameras. Since they do not have ground truth for visual comfort evaluation, their quality can be assessed using a subjective user study. We ask 10 persons to compare the results of our method with those of the other two methods. The comparison stereoscopic images are displayed side by side on a 27-inch LED screen in a random order, while each user is mounted with an NVIDIA GeForce 3D Vision glasses for viewing those images on a distance of 1 meter away from the screen. For each comparison, the users need to select the preferred image based on the subjective feelings. Especially, they need to answer the following 3 questions. For each participant, we calculate the times of selecting our results rather than those of comparison methods in the certified comparisons. On average, users prefer hours in more than 30 out of 35 cases when considering the image composition, visual comfort, or general visual quality. We also show the percentage of users selecting our results against others based on the general visual quality of the stereoscopic images for each image, which also implies that our method is superior to the others. On average, the percentage that users prefer hours over the combination of work 25 and regression is 88%, while the percentage that users prefer hours over the alliance of work 25 and mapping 26 is 92%. Here we show several examples of visual comfort comparisons on real images. As shown in second and third columns of the figure, the general rectification method focuses on reducing vertical disparity but neglects image composition. It also can be seen from the third column that the disparity mapping method inevitably introduces artifacts. Taken together, our method is more in line with the requirements of the application. Finally, we summarize our works as follows. In this paper, we propose a method to handle the application of casual stereoscopic photography. We utilize a unified reinforcement learning-based model to obtain the optimal stereoscopic images by iteratively adjusting the stereoscopic images and evaluating their qualities, which mimics human-like behavior in processing images. However, our framework still has several limitations. Training our model requires a large amount of data, and there is still a gap between the real data and our synthetic data. Besides, our approach currently relies on two-dimensional images without much consideration on three-dimensional applications. In the future, we would like to utilize the captured images from three-dimensional world to involve more three-dimensional information and thus to resolve more challenging cases. That's it. For more details, please refer to our paper. Thank you for watching.